All right, yeah, take it away.
Cool, thanks for the introduction. You guys can see my screen, right?
Yes.
Awesome. Okay, so hi everyone, I'm Jay, and I'm here to present to you our climate hack solution with Tony and Andy. We're all engineering science students, so yeah, let's dive straight into it. So to give you a bit of context on what this challenge was, I'm gonna briefly go over what the problem is and what we were assigned to do. So currently in the UK, energy grids use a combination of both solar and natural gas sources to keep their electric grid powered. But ideally, they'd only use the natural gas sources only when the solar production is too low. As of now, they have natural gas on permanent standby, hence only using solar as excess power. They don't have accurate enough forecasting right now to do this. And so what we could do, or the challenge would be to create a better near-term forecasting to reduce potential carbon emissions and reduce electricity costs for end users. So our challenge was given 12 images covering a 120 by 120 pixel region cropped from satellite images taken 5 minutes apart, accurately predict the next 24 images for the central 64 by 64 pixel area in the center, essentially creating a better nowcasting model. And the impacts of this could be tremendous. By minimizing the use of standby gas turbines, it could potentially lead to a substantial reduction in carbon emissions of up to 100 kilotons a year. And this could potentially be expanded into the world to reduce about 100 million tons of carbon dioxide in a year by 2030. And so I'm going to briefly introduce the data set that we were working with. This was kind of the data we were working with. This was the large satellite imagery over the UK, and the data was provided by Open Climate Fix, and we had about 2 years worth of data, so about 100 gigabytes to work with this.
And so basically the data was provided in a sort of weird format called ZAR, and that was pretty slow to load actually. So instead what we did is we took the data set and we split it into NumPy arrays so that we could get faster data loading. We decided to not pre-cut crops from these satellite images, instead opting to save the entire satellite image. This is because that when we pre-cropped the images, we got overfitting, so we decided to just randomly cut on the fly. We also chose to use global normalization instead of batch normalization because we didn't really try both, but we found that this was a pretty decent approach. I'll go next. Okay, so now we're just going to talk about one of sort of our baseline approaches that we're going to use to compare against all our other models, which is optical flow. So first things first, what is optical flow? So basically, if you're given 2 images, optical flow is sort of like the velocity vector for each pixel. So sort of how each pixel is moving across 2 images. So here on the left here, we sort of have an example of optical flow applied to a video of people walking across a field. So you see that all the pixels on the people, they have a velocity vector sort of approximating, the speed at which they're walking. And then everything else, because the camera is stationary, all these pixels are not moving. So that's sort of what optical flow is. So how can this be used for predicting satellite images? Well, satellite images are basically looking at images of clouds, essentially. So we assume that clouds are sort of evolving due to an underlying sort of wind field that's moving them. So an optical flow is basically a way to approximate what that wind field is. And we do this with a pretty naive approach, which is just to take all the previous average optical flows, take all the previous optical flows and then average them together. So essentially we take the optical flow of the input image 1 versus input image 2, input image 2, input image 3, etc. We take these, we average them together, and we assume that that's the optical flow of the entire output image set. One of the drawbacks of using this technique, though, is that it actually gives quite poor performance. But one of the positives is that it actually produces images which are quite realistic to the human eye. So I guess that's one plus. But that's sort of our baseline, from which we are going to be comparing. Okay. So next, we're going to be talking about one of the approaches we actually tried, which was called TRAD-GRU or trajectory GRU. So in order to understand that, we first need to understand convolutional LSTMs and convolutional GRUs. So, yeah, I'm going to assume that most people here understand sort of LSTMs, but basically, convolutional LSTMs are basically just changing LSTMs so that the cell state is like sort of has an image shape. So it has height, width, and a channel. And so too does the hidden state. So the hidden states and channel states are sort of like images now. And basically, another thing that's changed is that inside the LSTM cell, we now have convolution operations as well. And basically what this leads to is the hidden state of the future is basically sort of determined by a small neighborhood of previous pixels from the previous hidden state and cell state. Okay, go to the next slide. So basically, this isn't necessarily ideal. So as you can see on the picture on the left, the hidden state, so the future pixels of the hidden state are determined by the sort of same neighborhood of points in the past hidden states. So this might not be ideal when, let's say, you have a satellite image where like a cloud is moving across the screen very fast. So its hidden state representation, we might want to sort of direct that information to a different location rather than the same location over and over again. So that's what trajectory RNN sort of does. It sort of determines these connections dynamically so that it can model these sort of rapid movements. Unfortunately, one of the main drawbacks is that the training was very slow for this model, so we didn't actually get to train this model to convergence for the competition. But in the future, we're going to look at maybe training this better and actually comparing it to our current model.
Excellent. Just a quick time check, Theo.
Oh, no, you're fine. Go ahead.
Okay. So we're going to move on to some background slides in order to kind of introduce the method the model that we use for our final submission. So in this slide we see a UNet architecture. And what is a UNet? It's a convolutional encoder and decoder. And basically what a convolution encoder and decoder does is the encoder of the network, as you can see in the image, it basically computes progressively higher level abstract features as the receptive fields of the convolutional kernels increase with the depth of the encoder. So this final leads to a final latent representation at the bottleneck of the network. So from the bottleneck, the decoder part of the UNet computes the feature maps of increasing resolution from this latent representation to finally get to the final input resolution in order to get your final output. So what a UNet also does is it also takes the abstract features computed at different resolution levels and then kind of feeds these into the decoder via skip connections, which allows the decoder to integrate information from different resolutions into its final output. It makes a powerful baseline model for image segmentation and also for satellite nowcasting. Next slide. Another part of our final model is the vision transformer. So before I talk about the vision transformer, I'll just briefly introduce kind of the ideas behind what a transformer is. So a transformer is a sequence-to-sequence model, which means it translates a sequence of elements to another sequence of elements. And its core mechanism relies on attention. So the idea of attention is for each output element that in the sequence-to-sequence model, the transformer learns which parts of the input sequence is most important. So you can see on the graphic to the left, the output image there's a weighted kind of visualization of the attention that was learned by the transformer. So you see that it's learning that the first two words are very important to this output, so on. You can see the other weighted connections, and some of the later middle words aren't as important. The problem with a normal transformer applied to a vision task is that the memory requirements of attention and a transformer scales quadratically with the number of elements. So with an image with a large number of pixels, this memory scaling can become a very large issue. So the introduction of vision transformers allows us to, basically what it does is it patches the images. It separates the images into image patches. So like 2x2 patches, 4x4 patches. This way you limit the number of tokens that are being passed into the transformer. And this kind of, you're able to get over this quadratic memory scaling challenge. Next slide. So our approach is we use a transformer augmented UNet. So first, a UNet is a standard baseline for satellite nowcasting, and it's good at combining spatial representations at different resolutions. what it isn't good at is convolutions aren't able to model temporal relationships as well as global feature connections between. So for example, if you have a cloud that's at one side of the image on frame 1 and you want to model it from to the other side of the image of 24, a unit isn't very good at doing that because a convolutional kernel has limited scope. By adding a vision transformer in the bottleneck, as shown in our graphic, it allows us to model the global relationships between different image patches. So this is why we added the vision transformer and has improved the unit. It allowed us to improve performance upon our unit baseline. Next slide. Some other modifications we did is we used group normalization in our network instead of batch normalization. The idea behind this is basically, sorry, excuse me a second. Okay, yeah, sorry. So basically the idea is that in our input image, we stack each frame as a time step. So each channel in our input image is a different time step. So what this means is that each channel of our input will have a different data distribution. And to account for these differing input distributions across time steps, we group the channels into 12 different groups, which represents each time step, and we normalize separately across these 12 different groups. The other modification we use is depth point convolutions. What these are is basically a combination of depth separated convolutions, where instead of convolving across all channels, we convolve across only one channel at a time, and then we concatenate the output. And then after that, we use pointwise convolutions, which is basically regular convolutions that convolve across all channels, but only with the 1x1 kernels. This allows us to reduce our model size significantly from around 50 million parameters to around 15 million training parameters without a noticeable drop in performance. Next slide. Some other things we tried but didn't make into our final model. One is a channel-based attention module for modeling temporal dependencies. So what it does is use max and average pooling to kind of collapse the spatial dimension of the feature maps into a single value, and then does an attention computation across channels, which models temporal dependencies. The other thing we tried is multi-scale or multi-resolution vision transformers. These are basically blocks where we have multiple vision transformers that take in features at multiple different resolutions. And then you can use these as the encoder part of the unit or as a decoder, but we never had time to fully train these to convergence. Next slide.
Right, and so briefly talking about some of our model analysis. First of all, this is a chart that shows the performances of different approaches that we took compared to kind of optical flow and persistence. And the main pattern to note here is that our model falls off in performance slower. And this is because our model predicts and compensates for uncertainties in the future by just blurring and averaging the images. And hence this preserves accuracy, but does not make realistic predictions. Another weakness, or one weakness to our model, however, is that we have a lot of checkerboarding in our predictions. And
yeah, so what is checkerboarding? So checkerboarding is caused by the transposed convolutions in our output, or in our convolutional decoder. So basically, transposed convolutions are a method of kind of approximating or an inverse of the convolution operator, which kind of makes sense. The encoder uses normal convolutions, and we use decoders to kind of upsample, and we use transposed convolutions to upsample our images. Unfortunately, this can result in checkerboard artifacts when kind of the transposed convolutions overlap when striding. So you can see in the top animation how the transposed kernel is kind of overlapping, this creating kind of these concentrations of input signal in a kind of checkerboard pattern. A couple different solutions to solve it. One is to use something called a resize convolution. So you do upsampling instead of using a transposed convolution. You use traditional methods like bilinear upsampling or nearest neighbor upsampling, and then you do a regular convolution, which does not it does not upsample, so it doesn't suffer from the checkerboarding issue as much. Another approach is you can use non-convolutional based upsampling, like what we tried with the multi-resolution vision transformer. Use that as a decoder in one of our experiments that we weren't able to finish. Next slide.
Right, and something we also looked at was comparing our model performance in quartiles. And the main motivation behind this was to see what data our model was good at and bad at. And so within this, the quartiles, we analyzed both the absolute differences and as well as the use FFT to see how frequencies also affect our performance.
Yeah, so basically, just a brief background on FFT. If any of you have done like signal analysis, especially on sound, basically what FFT does is it takes an input signal and it decomposes it into a linear combination of its fundamental frequencies, basically. So you can actually do this with an image, as it turns out, and that's sort of an example here. Basically, it decomposes images into sort of different sort of frequency images. Oh, okay. So all you really need to know is that sort of frequency means like how quickly the image colors are changing between its neighbors. And in our diagram, in our FFT diagrams here, lower frequency features are going to be near the center and higher frequency features are going to be around the edges. Okay, so here we're going to talk about sort of the first quartile, so basically the images where the model performed the worst on. And so basically what we saw is that our predictions don't really predict high frequency features very well. So as you can see from the FFTs of our predictions, those sort of high frequency features disappear really quickly. Whereas in the ground truth, these features are sort of maintained. And you can really also clearly see that in the difference as well. All right, next couple slides, I guess. So this is just improving performance. And then finally, the sort of samples in which our model performs the best at, these are sort of samples which already have pretty low frequency features to begin with. So that way, basically, even though the model doesn't really handle high frequency features well, since the ground truth doesn't really have many high frequency features, the model performs well on these. And basically, sort of the reason why we think the model is sort of decaying these high frequency features is that, well, as stated earlier, we hypothesized that the model is taking a sort of average of all of the future possibilities. Can you go back to the first quartile slide? So if we take a look at the first quartile, if we take a look at the ground truth FFT, you can see that these high frequency features, they're sort of almost like white noise. So this is sort of like very randomized almost. So if you take an average of many of these, they're going to sort of almost cancel out. So these high frequency features are going to disappear. Whereas if you look near the center of this FFT, you see that these low frequency features are sort of almost constant throughout the entire time period. So if you average all of these possibilities together, that's going to remain constant, and that's what's going to be shown in the model. Okay, keep going. FFT, yeah, fast Fourier transform. Okay, and yeah, just potential possibilities to improve this sort of performance of the model on high frequency samples. One idea is to, instead of predicting the image itself, predict something like optical flow, because optical flow is actually relatively low frequency compared to the image itself. So that way the model might have a better time predicting that over time. And as you can see, we actually see this sort of performance enhancement a little bit in sort of even the baseline. So our current model here on the 6th frame, already these high frequency features are gone, but for optical flow, these high frequency features are preserved a little bit better. So that's just one possibility. Another possibility is to use something called adversarial loss. So if you've ever done stuff with a GAN or a generative adversarial network, there's something called a discriminator, which is basically trying to determine whether or not your predicted image is the real image or something that you've generated. So that way, the model is going to be forced to generate at least plausible high frequency features, because otherwise the discriminator would have a really easy time determining which one was real just by seeing if the image was blurry or not. So this will improve the sort of visual appearance of our model, but it might actually come at a cost to its real performance, because it can no longer use that technique of sort of taking the average of all these future possibilities.
Yeah, so we have some final takeaways, but I think we'll just wrap our presentation up here. If you guys have any questions about our experience, I think we can stay a bit after the whole meeting if you guys want to chat about it. Yeah, thank you so much for the presentation and for listening to our presentation. Yeah.
Okay, yeah, that's great. This is a lot of good work. You will leave questions to the end, so if anyone wants to stay afterwards, please feel free to do that, and then you can talk to the presenters in person. I think we'll move on to our next presenter. Preach, do you want to go ahead, share screen?
Let me just open up the PowerPoint.
Go for it. And if you'd like to give a quick, brief presentation or a brief introduction of yourself, that would be great too.
Okay. Let me just open this. Can you guys see this?
Yes.
Awesome. Okay. All right. So I am pre-mystery. I'm one of the people who participated at Climate Hack. Got a pretty decent score, I'd say. Also, I'm an EC2T2 for those of you guys interested in that stuff. And yeah, seems like everyone's an NSI here, so I'm representing the minority here. All right, let me put this full screen. Yeah, this is a bit more an orthodox presentation, but you know, I put this together in a short period of time. Just sorry, let me present this. Then I'll make sure my phone doesn't lock so I can actually read it. Okay, so I'll be detailing my attempt at Climate Hack in the short period of time I had. I had like a week and a half when I found out about this, so I was like, okay, might as well try out. So basically the problem is, like they're talking about solar panel, solar photovoltaic generation optimization. But essentially the problem for us is predict 2 hours of satellite imagery, satellite weather imagery based on a previous hour, and it would be at 5-minute intervals. So it's like 12 images per hour. So essentially your model, the problem would be taking 12 images of satellite imagery and predict the next 24 images of satellite imagery for the weather data. And yeah, that's the goal. And also it'd be for a small patch. So essentially the whole idea is you have a large area to predict for a small area, so it can predict what's happening at the edges. You get the information of what's happening outside the edges, and you can predict what's happening in the middle, essentially, based on the surrounding data. So my first attempt, well, yeah, also I have a lot of time, so I'm gonna be going over all my attempts over that week and a half. And yeah, so my first attempt was the basic dense model they had. It was very basic, but I made 2 changes. But essentially, this is the most brainy thing you could do. You just flatten your input, put it into a dense model, and reshape the output. So it gives you 24 images. And well, this doesn't look exactly this. It was like 3 layers instead of 2. I made 2 changes. So I made it wider, and I just made it wider. I just thought the original size was 512. I made it 1024. Pretty simple change. But then I also use sigmoid activation instead of ReLU at the output, because it just seemed like they were using ReLU at the output layer, which didn't make much sense to me, because you can just constrain the output. If you constrain the output, you can save your model from having to learn the range, essentially, which is a big improvement, I'd say. And yeah, I told this to my friend, like all I did was change it to sigmoid, and I got a pretty good result. And he's like, oh yeah, sigmoid's a great activation function, which I disagree with, but it's good for its range. So, and so the result of that was I immediately got above 60% or 6.6 accuracy. And the organizer was like, how'd you do that with such a basic model? I was like, I just put sigmoid in there. So yeah, that was a major improvement, I'd say, just from change activation. And I'll reuse this whole idea, this whole concept of just using sigmoid throughout the rest of my models. And then the next thing I would try is perceivers. So when I first saw this problem, I immediately thought of attention mechanisms, because based on what I knew at the time, they're good at capturing global relationships. And for something as complex as weather, capturing global relationships seems like a great idea. And then I read into the Climate Hack problem statement, and essentially they were advocating for perceivers. So I was like, okay, this is great. It's a mechanism, it's an architecture based on global attention. And the whole concept is attention mechanism, and it can take in whatever input you want and output whatever you want. So I was like, okay, I might as well just output in all the images at once, and then output, and then like essentially change this. See this? There's just something called the output query array, which tells you, which essentially gives the network what kind of size you want to output from the model. So I just changed this so that it would output 12. It would output 24. It would output a tensor that would be 24 images, and all you have to do is reshape the output in order to get those 24 images. So that was my first attempt, essentially. Just plug in everything at once so it can get all the relationships between the images at once. Do its processing in the latent space, which is this section over here, and create an output for those 24 images. Very basic implementation, very vanilla. Well, I guess I can go over a bit of how it works. Yeah, I just put in this latent array is learned over here. Essentially says extract whatever features are important from the input, from the actual input, which is over here. And then essentially it's basically a transformer internally. You just do a bunch of processing through basically what is a transformer layer multiple times. And then this output query array would extract the features that are relevant to the output. And there you would get your output array, and you can do whatever you want with that. In this case, just reshape it. And it was the results are pretty bad. I was like, what's going on here? And so I did a second experiment, which is basic classification on the perceiver, and just do fashion MNIST. And I even tried using like, there's something called the embedding space. Sorry, yeah, the embedding space, where you take your inputs and then you transform into a different space in order to allow for the network to do its thing in that space. And it can reduce the dimensions. It can essentially make it much smaller, puts it into a form that's much easier for network to understand. So I tried using convolutions for that, which improved my results, but the results are pretty bad. So I was like, the perceivers aren't going to work for this, I guess, at least with my level of understanding of them. And well, okay, I didn't put an S here, but anyway, yeah. So things I learned from this that might have helped afterwards. I learned this after the fact. So my latent spaces for the perceiver were quite tiny. I learned this afterwards during my little experiments during the competition. And so that's one thing that was wrong about my perceiver. And the second thing is that attention-driven architectures are usually better trained with the lamb optimizer and larger batch sizes. That's what they use in the perceiver paper, which I probably should have read the perceiver paper better before I tried it out. But attention-driven architectures can be quite difficult to train. So that would come up again during my experiments, but we'll see when that comes around. So yeah, I abandoned perceivers and went to the most brain-dead thing you can do, given that that convolutional layers exist and convolutional transpose layers exist. You essentially just stack convolutional layers in the encoder section, and then you put them into you essentially turn it into like a bottleneck, like you make a tiny latent array at the middle, and then you do a decoding, which you use transpose layers to expand the latent space back into an actual image, like actual image. Well, in this case, you accept 12 images at the input and 24 images at the output. So your channels would be the time dimension. And yeah, it's the most simple thing you can do with a convolutional layers. And I did pretty well with this. Like I got 0.68 on this, which was quite a big improvement. And yeah, just another side note, most of my models were trained for a very little amount of time, given how little time I had to experiment with all my models. Like I only had a week and a half, so I was like, I'm not going to waste too much time on training, which probably worked against me, but hey, it definitely did its thing. So I got a thumbs up for that one. And then this one was quite ambitious. So essentially, I was like, well, transformers are good at sequence to sequence problems, but they're not good at massive input spaces, which images would do. And I was like, what if we just take the images, put them into a latent space to represent them, essentially transformer will act on that space. So you'd have 12 latent, your sequence length for the input would be 12, but it'd be it would be 12 latent codes for each image at the input, and then the output would be 24 latent codes. And then the encoder decoder would do the whole mess of turning the images from and to this latent space. So essentially a transformer would act in the latent space. And yeah, this is my logic, good for sequence tasks. Latent codes are much easier to process, so yeah. And I could train the encoder and decoder separately. Problem was, essentially it wouldn't even fit on VRAM when I tried to train it. I probably could have done a simpler version of the encoder decoder and maybe got away with that. But in any case, I realized transformers were quite hard to train. So I basically gave up on attention mechanisms at this point. And I think I tried putting attention somewhere in my next model, which is UNets, but overall it didn't have a good effect. I'd say like it would take much, it would be much more difficult to get to attention mechanisms. So anyway, UNets are apparently the gold standard here for this competition. Like the winning team also use UNets, and so this is what I ended up using eventually. Towards the end of my time I had. So essentially a UNet, let me go back. A UNet is a series of convolutional steps which would do a lot of the processing, and then you have these downsampling, upsampling sections. And then the magic would come with the skip connections. So between each convolutional block, you would skip to transfer information to the next block on the other side. So you'd have your encoder section here and your decoder section here, and you skip to give some information to the next set of decoding layers on the other side, essentially. And skip connections, they appear a lot throughout like the ResNets and stuff. They tend to do quite a bit for at least image recognition, image tasks. So I had my vanilla UNet. I just essentially adapted it to accept 12 images and output 24 images, and give me 0.74 accuracy. And this was one of the bigger jumps I had in accuracy. And the simple thing I did was I made this section here deeper where the bottleneck is, and that gave me another % accuracy improvement. Now the thing is, it's such a small improvement. Maybe if I trained the UNet longer, the original vanilla UNet longer, I would have gotten better results. But it was like basically using whatever I could in the time I had. And then here's another ambitious thing I tried, which was UNet++. So I found this out in like a day or two before the end. And essentially what happens here is it's a whole mess of skip connections and convolutional processing layers. So all these nodes represent where you do your convolution layers, your typical convolution layers. And then you do your skip connections, which is these dotted lines over here. It's quite a mess to get working and even understand. So I'm not going to go too deep into this, but it was very prone to overfitting essentially. And maybe if I use the LAM optimizer, which is good for preventing overfitting, given it can handle larger batch sizes, maybe that would have worked. Or if I injected noise into each layer to prevent overfitting, maybe that would have helped in that case. But it was so prone to overfitting that by the time, like, I was training this in my last few hours, essentially, like this would probably get like 73% maximum accuracy before it started overfitting. So what I just went to my final attempt, which gave me my final highest accuracy. I had like 20 minutes left before I had to start uploading whatever I had. So I just took my best performing model, which I call the UNet deep model, which is the one with the deeper layers at the bottleneck. And then I took a LAM optimizer with a slightly higher batch size. And when I just trained it for a little time I had left, and that got me up to 76% accuracy, or 76 accuracy, yeah, 0.76, which was 14th place at the time of the first round end. And so yeah, that gave me a pretty good result. And if I understood the LAM optimizer better, I probably would have used a much bigger batch size, and that might have gotten me even better results given the time I had. And yeah, like this was my best attempt, I'd say, or this is definitely best attempt at the at the Climate Hack, which was UNets, and then used LAM optimizer to push even further, which was a bit of a desperate attempt, to be honest. I had such little time left, so that was my final thing. So key takeaways: tension mechanisms are hard to deal with, but UNets, they get you to the goal much faster. And also, like, given what your circumstances are, you should try your best, regardless of what the odds might be. Like, I had a week and a half to do all this, and at the beginning, basically nothing was working with my perceiver stuff, but I still managed to get 14th place at the time of the first round end. So I'm like, okay, I mean, I'll accept that. And also, turns out, I just wanted to say this. Turns out attention isn't all that magical as it turned out to, as we made out to be. I just want to add this. I discovered this right after competition. Apparently, attention isn't that magical. Like, they use use something called spatial gated units to instead of whole attention mechanism and transformers to achieve equivalent results in many problems that transformers are applied to. And then they did something with BERT where they compared it. It did slightly worse than BERT, but then they put in a little bit of attention and it did much better than what BERT did on that original problem. I just want to add that because I just felt lied to, I was like, wow, I thought attention mechanism was some great thing, but I guess not. Oh, sorry. Okay, I went up a little bit over, but anyway, I think that's my presentation essentially.
Great. Thank you so much, Preet. This was really interesting. Like, I really enjoyed the way you thought through your approach and then tried all these attempts, even with the amount of time you had. Yeah, I guess you did go a little bit over, but that's fine. Again, we'll direct questions at the very end. So that kind of wraps up both of the Climate Hack presenters. I hope you all found that insightful. Now we'll kind of shift with the timeout that we have left to members of the UTMIST community who are going to be presenting their own personal projects that they've worked on throughout the year. So Aditya, do you want to share screen? Maybe give us a quick self-introduction as well.
Yeah, I just have a few slides, so I'll share those.
Go ahead.
I'm Aditya. I'm a second-year student in CS, and I will be presenting. Can you all see this?
Yes, go ahead.
Okay. So I did a little implementation of some ideas I found in this. It's an older paper called "Distilling the Knowledge in a Neural Network," and I did a few implementations of the ideas that they presented in this because I thought they were kind of cool. It's relatively simple, and it still has a lot of basic concepts in it, but well, I'll get to it. But there's this one part of it that I think is really interesting. And I have a little blog post here. I guess I could share it later or something that goes more in depth into what I did and the results that I got. Okay, so let's begin. So we'll start at the very basics. This is just a softmax function. The point of this is just to turn some class scores into a probability distribution. You've all probably seen this before. Now, I will make a small modification to it where I will add this term T, which is called temperature, also known as softmax temperature, to the term. And I'm going to try, starting with, as you can see, if I have T is equal to 1, it just goes back to the regular softmax function. But what I'm going to do is I'm going to try and increase this T value and see the effects it has on just this vector that I'll give it. So just 1, 2, 3, 4. Let's see what it looks like. So at the beginning, it's as expected, it's just a regular softmax, but as I slowly increase the temperature, you can sort of see that it smooths out, and this is the same terminology that they use in the paper, it smooths out the probability distribution, because you can convince yourself that as this temperature here goes to infinity, eventually you'll just end up with a uniform distribution, which is sort of what you can see here, that as T gets very large, it kind of just evens out. Now, let's talk about this in the context of image classification. So this is just the image from MNIST. It is when I run it through my classifier, which is already pre-trained, and the pre-trained classifier has a very high accuracy, so it was trained to completion. The the softmax distribution is basically just assigns an extremely high probability to the 4 and basically zeros to the others, which is generally what we should expect. But now, what I'll do is I'll take that softmax with temperature and apply it to the output scores that my classifier will produce, and see what happens when I change the temperature value that I use. So temperature is equal to 1. It's the same as last time. The softmax function stays the same. It's just assigns a very high probability to the ground truth. But something interesting happens. So as we increase the temperature, as I showed before on that sample vector, the probability distribution sort of softens and eventually becomes uniform at very large values. But here's something interesting. So if we look at this, yeah, it's clearly a 4, but what else could it be? It sort of resembles a 9 in a way. And the interesting thing is, at a smaller temperature value, like 5, we notice that 9 actually has a higher probability than the other classes. Well, 4 is still like the highest, obviously, because that's what the image is, and the classifier recognizes that. But if we use temperature values, we kind of see other classes that the image could be. And this is a concept called soft labels, meaning we're not only just saying like, as opposed to the one-hot case where we just kind of one-hot encode the ground truth class, we're also sort of giving information in the information encoded in these labels is what other classes that the image could be, which in a way is more meaningful because it allows us to sort of better discriminate and classify between different images in the data set. So now I'll explain how this can actually be leveraged in training. So what we'll do is we'll train a teacher model. This is a pre-trained teacher model, as we had before, which produces these soft labels. So it's trained to completion on just the regular data set, but then we change the activation from regular softmax to softmax with temperature. And over here, that's what provides these soft labels. And we also provide the hard labels and then ultimately we get this loss function. So the first term here is just a standard cross entropy loss. And what we'll do is we'll use this loss to train a student model from scratch on the data set. So the first term is a cross entropy loss. This is for the student model, where we essentially just want to maximize the probability of the ground truth given these hard labels, which is just the standard case. Now, the second term is we want to use softmax with temperature to match the predictions of the student network to the predictions of the teacher network, but now with the soft labels. So rather than saying, okay, I want to match exactly what the ground truth is, we want to match the smaller probabilities to be higher to classes that are also likely, apart from the ground truth class here. So ultimately what this means is, and the paper showed this, was if the student network can be small, right? As you can see here, the teacher network is a lot deeper. The student network only has like 4 layers. The student network can be small, but with this scheme of injecting this additional information with the soft neighbors, it actually turns out that it can perform just as well as the teacher. And sometimes they showed that on certain tasks, it could do even better. So I implemented this. My GitHub repository is over here if you'd like to take a look. I'm just going to share some of my results. So the first thing, which I found very interesting, is I trained the teacher on the full data set, and I trained the student on classes 0 to 5. So meaning the student, like if I ran just a regular validation test on it, it would do like terrible on these 4 classes that it did not see during training. Now here's the interesting part. I used some hyperparameters here where I set my temperature to 10, and I set the weight here, alpha, to 0.9. And I noticed that the performance it had after it was trained on this soft label task was, or with this new loss on the classes it hadn't seen, were pretty good. Even though it was not directly trained on those classes during training, the fact that on samples from these classes, and with the soft labels, gave it enough information to distinguish between images from the classes it was trained on and the classes it wasn't. So its accuracies were actually pretty good, even though it never saw those on training. And note here that the student is smaller than the teacher in this case, because here I just did a standard run where I set temperature to 1, so just a regular softmax, and I set the weight of that auxiliary loss term here to not matter at all. So then what ended up happening was it ended up getting these accuracies on all the classes. But then when I threw in temperature by raising it and changing the weight of that part of the loss term with the soft labels, it ended up doing actually a lot better, even though it was it's smaller than the teacher in a way. So ultimately, with this ablation test, I'm able to show that the student network is able to learn better with these soft labels, and also, interestingly enough, it's able to learn to recognize classes that it didn't see during training. That's all I got.
Thank you so much, Aditya. This is actually really interesting work. I can definitely see how perhaps you can use this to, I guess, improve like the performance of a model if you have like limited data or even like some transfer learning settings. This is really cool. Yeah, I guess to everyone, make sure you check out that GitHub too. I think this is a really good resource and a really great paper. Very fitting for our substitute of the paper reading group. So now we only have 3 minutes. So hey Tab, I don't think we'll have time to get to you. That's okay.
Yep, that's perfectly fine.
All right. Oh yes, and Tony, yes, I will be posting the recording onto YouTube, and we will send an announcement to the UTMIST announcements channel once, or maybe not announcements, but we'll send it to one of the channels when it's up. And in terms of sharing the slides, if you would like those to be public, you could pass them to me, and then when I share the recording, I'll also include the links to the slides there. So just let me know. Okay, yeah. So we have time for questions, and of course, you all can stay later after. I guess we'll just make this a free-for-all for anyone. So I'll just open the floor. If anyone has questions to a specific presenter, just unmute and ask away. Okay, if there's nothing really immediate, I'd like to ask something to Aditya real quick.
Yep.
So for the temperature value, how is that normally set? Is that like because like when we have the teacher model, right? Like I assume the temperature is essentially a hyperparameter in this case, right? So
Yeah.
does the performance get impacted a lot by the amount of temperature we add? And if so, how much do we, or how do we really tune that?
Yeah, so when I was doing this, I didn't really know like what was good or not, so I just ran a grid search.
Okay.
So I had like a couple of configs where I would search like certain values, and I noticed that like I don't know if you remember, but at the high temperature values, it essentially becomes a uniform distribution. And that isn't really informative, because you're just like saying, oh, when the temperature, like for any distribution you give it, regardless of the probabilities there are, it will converge to a uniform if the temperature is high enough. So at that point, it isn't really doing anything. But then if you set it like, generally lower values worked, because I can just share my screen again quickly. Like generally lower values worked because they didn't make it so that a lot of information was lost as the higher values would show. But yeah, mostly it was just like a grid search. Like I figured out values between 2 and 10 worked best. And I would just set it, I would just like try some values and I'd pick which one works best for each student model. So
I see. I imagine this might be proportional to some classes too, because MNIST only has 10 classes, right? So it kind of makes sense that scaling it down to a factor of 10 might keep it in like a more reasonable distribution. If it's a lot, I think if the temperature is a lot higher than the number of classes, then I guess like the exponent becomes naturally just smaller, much smaller, right? So then we tend to get uniform. So I'm curious to see how this would generalize to a bigger data set, perhaps maybe to like ImageNet or like something similar to that.
Yeah, that's what I wanted to try next, because in the actual paper they did MNIST, but then they also did CIFAR.
Right.
But then that would, so yeah, I wanted to try something like that over the summer, where I would implement like a convolutional encoder and classifier. So rather than, because this is just, I just did this with like regular MLPs to see that. The thing I wanted to test was that this implicit learning thing works for like you can classify classes you haven't seen. But yeah, that's something I was considering doing next. So trying it on like RGB with more classes and such.
Yeah, this is definitely very interesting. I think there's also a bit of parallel with this to the idea of I guess it's called like model stealing almost. So like given like a model's predictions, you can actually kind of train a model or your own model to steal the other model's predictions, and it also kind of learns the other model's features. So I feel like this could be quite similar, at least in terms of how it's done. It's similar to having a teacher model, right? Except in this case, the teacher is unwilling.
Yeah. I haven't seen the model stealing stuff, but the only information that the students really taking is like their predictions. But I'd assume like there's ways to leverage the information inside of the like, I guess maybe intermediate layers or the weights themselves to maybe figure out like distill more than what they're trying to do in this paper.
This is certainly a great paper to present. I like it.
Yeah, it's pretty simple, but the results are kind of neat.
Your insights. I also have a question for, I guess, Tony, Jay, and Andy. Any of you guys want to share your screen again? Okay, actually, just you don't necessarily have to share
the presentation. Sure.
Okay. I guess one thing I want to ask is like, what elements of the data kind of motivated you to select your model? Like, was the model simply because of trial and error? Like, I'm sure there was probably some theoretical grounding in how you decided to proceed, right?
Okay, so I guess from my end, a lot of my model choices and initial approaches, like what's in the presentation isn't everything that we tried, obviously. But one thing is that I think the main motivator was just I went through a bunch of like extensively through the literature of similar problems, as well as with satellite nowcasting and like other similar problems. Like, so this we're looking at cloud coverage, but there's a lot of stuff on like precipitation forecasting and other similar things. So I say I didn't really look too much into like I didn't like analyze the images per se too much, like the data set itself, but I more so looked at the general problem and what kind of models we use, and I try to either adapt different implementations and try them out, and then kind of mix them together and try different like techniques that I see in different papers. It's kind of the approach I went. I think Jay and Andy potentially had a different approach.
I think we basically did the same thing. We just
like at the beginning, we just kind of scrounged the literature and saw what common approaches were to these types of problems.
Yeah.
Okay. Yeah. Was your final approach very similar to any of like existing solutions in the literature, or is it a lot more novel and like handcrafted?
Yeah. So our final approach is like the UNet with a vision transform in the bottleneck has been done in literature. Right. It's pretty similar. Obviously, like some of the techniques that we added are kind of come from different papers, so it's not like a single paper include everything. Like stuff with the depth separated convolutions.
Right.
Some of the other stuff, group normalization. Some of the more novel stuff we tried, we just didn't have time to train it. I think one of the biggest things is that our data like loading thing is a little inefficient. Like, our training speed wasn't greatest. If I was to do it again, I would optimize our training pipeline, because I think the biggest just bottleneck in our like development and our iteration process was just how long it took to train the model to see how well it does. Because like our best model is still improving, and then it's hard to verify if your new approach is any better because it's never catching up, because it takes forever to train.
That's true. I feel like that's like a general like bottleneck for a lot of machine learning though, is just training
Yeah.
up the model, right? Okay, but it's great to see that you added like your own little flavors from other different resources into your model. I think that's also how a lot of innovation is done, right? Like I think a lot of papers, for example, the I guess what was it, like the AlexNet one? They had like convolutions, but they also had their own little additional tricks to just improve that actually just a little bit more. And I think in your case, it definitely paid off too. So yeah, very great work.
Thanks. Yeah, I actually have I mean some I guess things to talk to create I guess actually a lot of it's interesting to see your process and how it differed or is pretty like similar to some of the things that we looked at. I was curious about the LAM optimizer. I actually didn't see. I guess I didn't go through the perceiver paper close enough as well. Do you know? Can you comment on like? I don't know too much about the LAM optimizer. Why is it like so much better for training attention-based like models compared to like Atom or something like some Atom W or something similar like that?
I'm actually not 100% sure why it's better. I know it's like it's essentially Atom, but they do like they take the direction of the parameter, the direction which the gradient is telling the parameters to go, and then they take the they do it for each layer. They scale the step for each layer based on how big the parameters are at that moment, I think, like how the magnitude of the parameters. But I don't know exactly how it works much better. I know it's if you're using much larger batch sizes, it's LAM optimizer is the way to go, especially since larger batch sizes can lead straight to go straight to your the best minimum, I think. But yeah, I don't know why it's better for attention architectures. It might just be that's a superior optimizer, especially when using large batch sizes. And it might just be that attention mechanisms are just harder to train, so that it's just much better to use a larger batch size and use LAM optimizer to prevent the overfitting problem. And yeah, that's what I think.
I see. Cool.
That's a good question.
Yeah.
Okay, great. Are there any more questions? All right, if not, I will be ending the recording here. Thank you all for coming and presenting for the presenters at least. I hope you all learned something today, and this was probably going to be the last paper reading group for this year. We hope to start something else similar next year, perhaps even have another venue to host these kind of small product showcases throughout the year. I think these are very insightful and really give an insight into what the members of the UTMIST community are up to. So it's great to see everyone coming out to this, and I hope to continue this in the future. So yeah, I'll stop recording now.